Okay, we're going to be looking at Chapter 5 today. Uh, Basic atomic structure, what's an atom, history of the atom, and a really simple look at the periodic table, broad strokes. We will actually do an entire unit just on the periodic table later this year. Okay, so atoms. The first historical record we have of the atom came from an ancient Greek philosopher by the name of Democritus. Now, the idea behind this is that because he was a Greek philosopher, he didn't actually need to do experiments. He just had to sit around and think about stuff. A cushy job, I believe. And the idea behind this is that he was thinking, okay, if I take a piece of matter like a piece of paper, I can rip it in half, and there's still paper, just smaller. And I can rip that in half, and it's still paper, just smaller. And he thought eventually, if I just kept ripping the paper in half, or imagined ripping it in half, that I would reach a point where I could not rip it anymore. And so this led him to believe that matter was made of these tiny, indivisible, indestructible particles of matter that he called an atom. And the word atom actually comes from the ancient Greek word atomos, meaning indivisible or unbreakable. Because he thought there's that little particle that was just too small, he couldn't break it down anymore. But there is really no evidence for this, because again, he was an ancient Greek philosopher, just kind of sat around and thought about things. So we really couldn't do much about this. It was taught in schools as kind of a side note for hundreds of years, if not thousands. Definitely over 1,000 years. But again, couldn't really do much with it. Now, this was until there's an English school teacher named John Dalton who was actually performing experiments, and he gave us the first scientific model of the atom. And what he was doing is he was trying to learn in what ratios different elements combined in to make compounds in different chemical reactions. And he kept finding that there was this whole number that kept appearing, this whole number in ratios. And this led to what is known as Dalton's atomic theory. So the first real explanation of what goes on in a chemical reaction and bringing in this idea of atoms. So Dalton's atomic theory. You need to know these pieces. One, all elements are composed of tiny particles called atoms. So again, he started seeing these whole number ratios. And he said, okay, there's that atoms. There's that thing goes back to Democritus. Two, atoms of the same element are identical. The atoms of different elements are different. Pretty self-explanatory. That's what he felt at the time. Three, atoms of different elements can physically mix together or chemically combine with each other in simple whole number ratios to form compounds. So again, he started seeing these whole number ratios appearing when he was reacting elements together. And he kind of figured, okay, since I'm seeing these whole number ratios, there has to be something whole. There has to be something fundamental. And that's what led to this. This is what led to the idea of atoms. And finally, he explains what a chemical reaction itself is. The chemical reactions occur when atoms are separated from each other, joined together, or just rearranged. But what doesn't happen is that atoms of one element are not changed into atoms of another element during a chemical reaction. Um, so this is a theory because it's explaining what we're seeing. So it's explaining how a chemical reaction happens. It's explaining what a chemical reaction is, and in doing so, brings in this idea of atoms. A lot of important information on this slide. Now, a way to kind of think about this is imagine, kind of like Democritus did, imagine a pure copper penny, which we don't have anymore. Pennies nowadays are a thin layer of copper coating zinc. But pretend it's a pure copper penny and grind it into a fine dust. Because it's now copper dust, it still has the same properties as the original copper penny because they're both the same substance. And again, same substance, same properties. And keep dividing those grains finer and finer and finer. What Dalton says, and Democritus would agree with to some extent, is that eventually you'll get to a particle of copper so small that it could no longer be divided and still be copper. Again, a little bit different here. We're saying if you divided it anymore, if you made it any smaller, it would cease to be copper. Not that we just can't divide it, it just wouldn't be copper anymore. That final particle of copper would be an atom of copper. And an atom is defined as the smallest particle of an element that still retains all the properties of that element. And really, I would highlight the uh, atom definition there because that's important. And you can view this model like a billiard ball. So that's kind of the mental model that Dalton had. Think of a small ball, so ball shaped, spherically round, neutral, uniform throughout. Oh, there's what I wanted you to highlight. Size of atoms. How big are atoms? They are very, very small. I know that is an unsatisfying description, so I'll give you some numbers. So, a pure copper coin the size of a penny would contain 2.4 times 10 to the 22nd atoms. Now, those of you who are good at scientific notation may look at that and go, wow, that's a really big number. But numbers after about 1,000 or so really become pretty meaningless to us. So let's give some analogy to this. So comparison, Earth has somewhere around 7 billion people. That's what we see there. Look at that exponent. That means that there is 4 times 10 to the 12th more atoms in a little coin than people on Earth. So again, that means you would need 4 times 10 to the 12th Earths worth of people to equal the atoms in a coin. What's interesting, and I think interesting, is that even though atoms are so small, we can still see them and see them pretty well. So that leads us to section 5.2. So what's going on with the structure of these atoms? So it turns out that Dalton was pretty right, but a little bit off. And that's what we expect with scientific models, that they change over time. We get new evidence, we refine it. Turns out atoms are divisible. We can break atoms down into smaller, even more fundamental particles, but the definition of the atom is still fine. The atom is still the smallest piece of the element that keeps the properties of that element. If I break down an atom into smaller pieces, those smaller pieces do not share the same properties. And right now, this is actually the cutting edge of chemistry and physics, is that there's no single model that accounts for all the subatomic particles that are known about. But we're going to work with the simple ones. So we're going to focus on the 3 basic subatomic particles: electrons, protons, and neutrons. So, starting with electrons. So electrons all have a negative charge. And they're discovered by J.J. Thomson in 1897. And basically what he found is that atoms contained a negatively charged piece to it. What he ended up doing is called the cathode ray tube experiment. He took a gas, electrically charged it, and found that this glowing line would appear. And if he connected two electric plates on either side of the beam would, one positive, one negative, the beam would always curve towards the positive. And we know that um, positive and negative attract. We know negative and negative repel. So he said, okay, there's something in that atom that has a negative charge because it's being repelled away from the negative, being attracted towards the positive. We say that each of those particles has 1 unit of negative charge and is much lighter than a hydrogen atom, almost 2,000 times lighter. This gave us what is called the plum pudding model of the atom. Now, when I first heard this, and I heard this for years, I always wondered what the heck plum pudding was. I was imagining like Jello pudding with plums in it, and that just sounded disgusting. Because I was told like this, it's a solid ball with charges scattered throughout, like raisins in a plum pudding, which then further confused me because I went, what are raisins doing in plum pudding? Why isn't it raisin pudding? And I got confused and frustrated and moved on. This was until a few years ago, I was actually watching a cooking show, and they're talking about that at this point in history in England, where J.J. Thomson was from, is that pudding would refer to pretty much a baked good. Nowadays, pudding really means dessert, but at that point it was kind of a baked good. So we call this officially the plum pudding model of the atom. Think of it more like the chocolate chip cookie model of the atom or the blueberry muffin model of the atom, where you have your batter and then you have chocolate chips or blueberries scattered throughout it. Those blueberries or the chocolate chips, those would be the electrons in the atom. And I think that makes a lot more sense. Much later in the 20th century, Robert Millikan calculated the correct mass of an electron to be 1/1840th the mass of a hydrogen atom, or about 2,000 times lighter, as I said earlier. Now, this caused a bit of a problem, this discovery of the electron, because Dalton knew, and we still knew at this point, that atoms have no charge. They are neutral. So how can atoms be neutral if they have this negative piece to it? Well, we know that positive and negative cancels out. So if there's something with negative charge, there has to be something with positive charge. And we call that particle with a positive charge a proton. Finally, in the 20th century, Sir James Chadwick found the third basic subatomic particle called a neutron. This was discovered much later because the neutron is a wily little bugger. The neutron has no charge, which is why we had trouble finding it. It's about the same size as a proton, and what we're going to find out is that's actually located with the protons. So neutrons were kind of hiding amongst the protons. But together, the neutron, proton, and electron make up the building blocks of atoms. Now, just for the sake of completeness, we wonder, okay, if atoms are made of protons, neutrons, and electrons, what are protons, neutrons, and electrons made out of? And the answer to that is particles called quarks. And then we wondered, well, what are quarks made out of? And that's where chemistry and physics is right now, trying to figure that out and trying to find an explanation for that. Again, if you like tables, there's a table on page 111 of your textbook that kind of lists out the properties of these subatomic particles. If you hate tables, then avoid that, and probably you're going to have a hard time in life because, you know, we sit at tables, we eat at tables. Tables are pretty much everywhere. Now, even before neutrons were discovered, we want to know how the atom was put together, not just that there are electrons, there are protons, and we call it good, but how are they structured? So, I believe he was British. I think he was a physicist, but he could be a chemist. The line was a little bit blurred at this point in history. A guy by the name of Ernest Rutherford and his colleagues test this by doing something called the gold foil experiment. And what this was, he took a very, very thin piece of gold, and from what I understand, they chose gold because gold is particularly non-reactive. They didn't want chemical reactions to be a part of this. and they fired alpha particles at it. Alpha particles they knew were these relatively large, positively charged particles, and they fired the alpha particles at the gold foil. Now, because atoms are overall neutral, it was expected that the alpha particles would pass right on through. But, as you might be able to guess, that is not what happened. So what happened is kind of what we see here with this diagram. You have your alpha particle emitter here, and it's firing the alpha particles at the gold foil. And they started scattering, but not a lot. Only some started scattering. Some started scattering at very light angles. Some were actually bouncing backwards almost entirely. So this made them re-look at what's going on kind of in the atom itself. So what do we see happening here? Well, most of the particles passed through like expected, but a small amount bounced back. And they had to kind of explain why this was. Well, let's think through this logically. Alpha particles are positive. They knew that. The alpha particles were being deflected by something. That meant that they were coming in contact with something with a positive charge to repel them away. Now, we kind of have to think about the size and the mass that we're dealing with. Since most of the particles passed right on through, this meant that whatever had that positive charge had to be pretty small. The bigger it was, the more particles would have been deflected. But only since a small percentage were deflected, whatever they were hitting had to be pretty small. But because they're being deflected so severely, whatever they're hitting had a substantial amount of mass. They're hitting something pretty heavy. So all in all, this said that there was a lot of mass and positive charge in a really small area in the atom. And we call that small area in the center of the atom, where all the positive charges and a lot of the mass, we call that the nucleus. Not to be confused with the nucleus in biology. So, the nucleus. Again, the nucleus is the central core of the atom. We now know that's where the protons and the neutrons live, and that's why so much mass is there. And how much mass is there? So the nucleus is so dense that if you had a nucleus the size of a pea, it would have a mass of about 250 tons, which is incredibly dense. In fact, it's really the second most dense thing in the universe. The only thing more dense than a nucleus is a black hole. Now, how small is it? So we say it's small and it's dense. It's so small that if you had an atom the size of a football field, the nucleus would be about the size of a marble sitting on the 50-yard line. So, since the nucleus has only positive charge and takes up a small area, what's in the rest of the nucleus? So again, if we imagine our football stadium, or football field, you have a marble in the center. What's going on with the rest of it? What's in the rest of the atom? Well, that's the electrons. It's mostly empty space. Most atoms are empty, just nucleus in the center, very, very small, and some electrons whizzing about, even smaller than the nucleus. Which kind of gives us the Rutherford, this is also called the Bohr model, we'll find more about that later, model of the atom. So we have the nucleus in the center, and then you have electrons surrounding it. Okay, so distinguishing between atoms, section 5.3. Now, I want you to remember that Dalton said that atoms of one element are different from atoms of another. That's still true. But we want to ask how are they different? And it turns out they differ in the number of protons. So what we actually find is it's the number of protons that actually defines what element we're looking at. So for instance, A carbon atom is a carbon atom because it has 6 protons. Every atom with 6 protons is carbon. If we go to a distant planet and we find an atom with 6 protons, we go, oh, there's carbon. That is kind of what defines the different elements is differing number of protons. Oxygen is oxygen because it has 8. All oxygen atoms have 8 protons. That's just how it works. Now, because chemists like to make things difficult, just really job security, they have a term called atomic number. The atomic number is simply how many protons an element has. So all carbon atoms have 6 protons. All carbon atoms have an atomic number of 6. That's just all that it is. And remember that because atoms are electrically neutral, an atom will have to have an equal amount of protons and electrons. So in a normal neutral atom, if something like carbon has an atomic number of 6, that means it has 6 protons, which also means it would have 6 electrons. So pretty straightforward there. Okay, now things start to get a little funky. Mass number. So again, most of the mass of an atom is in its nucleus. Again, electrons are almost 2,000 times lighter than a proton or a neutron. And the nucleus contains, again, the protons and the neutrons. So the sum of the protons and neutrons in an atom is called its mass number. Every atom has a mass number, and it's simply the number of protons plus the number of neutrons in that atom. Now, how can we use this? So if you know the atomic number of an element and the mass number of an element, you can now find out what its structure is. So for instance, if I have an oxygen atom with an atomic number of 8, because all oxygen atoms have an atomic number of 8, and I tell you that its mass number is 16, well, what else do we know? Well, if the atomic number is 8, that means it has to have 8 protons. Since it has 8 protons, it also has 8 electrons. Now here's where the mass number comes in. We know the mass number is 16 because that's what we're told. The mass number is protons plus neutrons. So we go, okay, we have 8 protons, so what plus 8 equals 16? And that would also be 8. Now, are all the numbers all going to be the same every time? No. That's just a happy coincidence in this case. You can actually use this equation here if algebra is not kind of your innate language. So you can say that the number of neutrons will always be equal to the mass number minus the atomic number every time. So how can we shorthand this? Because again, as chemists, we are efficient, not lazy. So we can represent any specific atom by using its chemical symbol from the periodic table and 2 additional numbers written to the left of it. We write the atomic number as a subscript on the left. Subscript means below, so down and to the left of the symbol, we can write the atomic number. The mass number we write as a superscript. That means up. So up and to the left, we write the mass number next to the atomic symbol. So here's some examples. So all of these are shorthand ways of symbolizing specific atoms. So we can see here this bottom number in each case is the atomic number, and the top number in each case is the mass number. And if I want to find the number of neutrons, how do I do that? We just subtract them. And I actually like this format because it makes it very easy to do the subtraction. It looks like it's a subtraction problem to just subtract the bottom number from the top number. That gives you the number of neutrons. Okay, now we are dealing with this topic called isotopes, a little bit trickier. So, most of Dalton's atomic theory, still good and dandy, used today. But there are some issues. Dalton said all elements or all atoms of a certain element are the same. Turns out that's wrong. That different atoms of the same element can have different atomic structures. So let's think about what can differ. Can the protons differ for the same element? No, because the protons are what defines the element. So can the electrons differ for a normal neutral atom? Well, no, because to be neutral, the protons and electrons have to be the same. So that only leaves us with neutrons. So we find the number of neutrons can vary from atom to atom of the same element. And we call those variations isotopes. Now, this is a weird kind of topic. Think of the word isotope like we do the word flavor or version. Um, so what do I mean by that? So think about like ice cream. Ice cream comes in lots and lots of different flavors or versions. And those would be like isotopes. So maybe one isotope of ice cream would be chocolate. One isotope would be vanilla. One isotope would be bubblegum. So in the element, quote unquote, of ice cream, there's different versions of it, which are the different flavors of it. That's kind of how isotopes work. They're just different versions of the same element. So, because isotopes have different number of neutrons, that's what differs between them. They also have different mass numbers, but their chemical properties are the same. Because their protons and electrons are still the same. So that means a carbon with 6 neutrons and a carbon with 8 neutrons chemically acts the same. And the way that we usually represent these different isotopes is we write the name of the element, a dash, then their mass number, which I will show you on the next slide. So we can see here. So if I have a carbon with 6 neutrons, so carbon always has 6 protons. So 6 protons plus 6 neutrons makes 12 as its mass number. So we would write carbon 12 as its shorthand for the isotope. If I have a carbon with 8 neutrons, it would now have a mass number of 14 because 6 plus 8 is 14. So that'd be called carbon 14. And we have some other examples here. Hydrogen has 3 isotopes we use. Interesting note, I think it's interesting at least, that the hydrogen actually has specific names for its different isotopes that you don't need to know. So hydrogen with 0 neutrons is what we normally call just hydrogen. Hydrogen with 1 neutron we call deuterium. Hydrogen with 2 neutrons we call tritium. Just throwing that out there. Next is atomic mass. So we want to know the mass of atoms, but they're too small. You can't just put a single atom on a scale and go, oh, that's its mass. So we've had to create a scale for measuring atoms that works for us. Because again, grams are too big, scales don't work. We need something special for atoms. So we come up with a new mass unit, and it's all based on carbon 12. Arbitrary decision. And what we've done is we've said the mass of a carbon 12 is defined to have exactly the mass of 12.00000 AMU. And you might be wondering right now, well, what the heck is an AMU? It is not a flightless bird. That's an emu. No, an AMU, or atomic mass unit, is defined as 1/12 the mass of a carbon 12. Or, to put this in perspective, the atomic mass unit is the unit of mass for an atom. Now, this piece here is just some behind-the-scenes trickery. So we say carbon 12 has a mass of 12. So the atomic mass unit, or the mass in AMU, is simply just the mass of the atom. It's the mass number. So using AMU, that means that helium-4 has a mass of 4 AMU. Nickel-60 has a mass of 60 AMU. So when on the AMU scale, the mass number is the mass of the atom in AMU. Because we say that each proton and neutron has a mass of 1 AMU. That's how we make that. Now, on the periodic table, we should see atomic mass being a whole number. Protons and neutrons added together, the mass number. And we can't have fractions. But that's not what we see. On the periodic table, there is atomic mass of the elements, but that's not whole numbers. So what's going on? What's happening is that most elements occur as two or more isotopes. And the number that's on the periodic table has to be for the element as a whole, not just one particular isotope. So the atomic mass on the periodic table takes into consideration the masses and the percent abundances of the different isotopes. And by percent abundance, I mean that for an isotope, for one element, maybe one isotope, it has a percentage of 99%. That means 99% of those atoms is that particular isotope. And so again, the atomic mass on the periodic table has to take into consideration these higher and lower masses of these other isotopes. Now, what's fun is if you round the atomic mass on the periodic table to the nearest whole number, that will tell you who the most common isotope is. So, for example, if you look at carbon's atomic mass to the nearest whole number comes out to be 12. So that tells you that the carbon-12 is the most common isotope of carbon. How do we find this atomic mass? It's a little funky because you can't just take the average of the isotopes' masses. So for instance, chlorine has two major isotopes, chlorine 35, chlorine 37. If I took the mean average between them, I would get 36. That's not what we see. So if you look at the periodic table, you'll see that chlorine does not have an atomic mass of 36. What you have to do is take what's called a weighted average mass of the atom. So atomic mass is what's called a weighted average. And what a weighted average is, kind of like your grades are weighted, is it gives more weight, more emphasis to the element that has a greater abundance. So if I have one isotope or isotope with greater abundance, so if I have one isotope that's 98% abundant and one that's 2%, the mass of the 98% abundant one is going to have more effect on the atomic mass of the overall element. So you are going to be expected to calculate the atomic mass. To do this, you have to be given three pieces of information. I will provide you with these three pieces of information on the opportunities. That's what you're going to see. So here's how you do it. I'm going to walk through with an example. So some unknown element giving you a problem. This is very similar to what you're going to see on an opportunity. Two natural isotopes. One isotope has a mass of 69.956 AMU, relative abundance of 60%. The other isotope has a mass of 70.954 AMU, has an abundance of 40%. Find the atomic mass of the element and name it. Now, I know some of you are thinking right now, wait, Mr. Anderson, aren't mass numbers, the mass is supposed to be whole numbers? Because it's protons plus neutrons? And the answer is yes. These are not whole numbers because these come from experimental data, so there is error involved in that. That's okay. So what we're going to do is we're going to multiply each mass, its AMU, by its abundance in decimal form. I want to stress that. We're going to take the mass. So we're going to see here, we're going to take this mass, and I'm going to multiply it by this abundance in decimal form. So how do you turn a percentage into decimal form? Divide it by 100. So I'm going to do the 68.956 times 0.6. We're also going to take the other mass and multiply it by its percent abundance as a decimal. That's what we have to do. Then what do I do with all of that information? You add it together. Pretty simple problem. We're going to take the mass, multiply it by its percentage as a decimal, add the numbers together. So let's look at this problem. So first one, 68.956 times 0.6 gives us 41.3736, but we have to pay attention to significant digits. I only have 3 significant digits for my percentage, so that's all I'm allowed in my answer. I do the same thing with the second mass. I get my answer. I add them up. There we go. That is the atomic mass. Now, we do want to find out what element this is, so we look at the periodic table. What element is that most likely going to be? We find the element that has an atomic mass that matches most closely, which would probably be gallium. Okay, so now we're going to look at a basic structure of the periodic table. So a little bit of history. So by the mid 1800s, there'd been about 70 elements discovered, but it was just a bunch of disparate information. There was no overall pattern. There was no way to organize this, so that became a problem because we like patterns. We like trends. It means you have to memorize less. So scientists around the world were trying ways to find similarities between these elements to create some patterns. The person who's most successful with this was a Russian chemist by the name of Dmitry Mendeleev. And as story goes, what he did is he wrote down all the information that was known about the 70 elements that were known on onto cards, and he arranged them in vertical columns in order of increasing atomic mass. And what he noticed was this periodic or regularly repeating pattern of chemical and physical properties. So he rearranged the columns so that elements with similar properties were side by side with each other. This led to the creation of the first periodic table. It's called the periodic table because periodic or period means to regularly repeat. And it was repeating so that elements with similar properties were next to each other. And this was powerful because you no longer had to memorize the properties of every element. If you knew the properties of one element and you saw that there was elements next to it, you go, oh, they're similar. They have similar properties. This was became a very powerful tool. In your textbook is a picture of Mendeleev's periodic table. I also have an illustration of this on the next slide. So we can see here, this is kind of a picture of Mendeleev's original periodic table. And again, the way it was set up is that elements side by side with each other had similar properties. So we see here like lithium, sodium, potassium, rubidium, cesium. Those all had similar properties, so they were side by side with each other. Now, it's interesting about this, and what was very, very powerful is that there was these blank spaces throughout. That is a terrible drawing. That's why if you're trying to draw on this with a mouse. Anyway, so all these blank spots, and what he said, he left these blanks on purpose. He said, I predict that those blanks are elements that exist, but we haven't discovered yet. And that became kind of a challenge. And what set his periodic table apart from others trying to do this very similar work. And what's interesting is every single element that he predicted was found with the properties it was predicted. In fact, there's some stories of people publishing papers saying, hey, we found this element and it doesn't match Mendeleev's table. And Mendeleev would basically respond with, you're wrong. You're wrong and you're dumb. And it turns out that in every single case of that, the person was wrong. Not sure they're dumb, but they were wrong. Mendeleev's table really survived the test of time. Now, the periodic table stuck around for a while until 1913. British physicist by the name of Henry Moseley figured out how many protons were actually in atoms. Which we knew that protons existed, we knew that electrons existed, but it wasn't until 1913 we could figure out how many. And what he did is he rearranged the periodic table by order of atomic number, not atomic mass. Mendeleev's periodic table was by atomic mass, and that did create some weird inconsistencies that people had trouble with. But when he arranged it by atomic number, those inconsistencies kind of smoothed out. So this gives us the modern periodic table. And we tipped it over on its side so that elements that were similar are no longer side by side, left and right with each other, but now elements that are similar are up and down or in vertical columns with each other. So the modern periodic table. The horizontal rows of the periodic table are called periods. There are 7 periods on the periodic table, kind of like the number of periods here at Anacortes High School. A coincidence? Perhaps. The vertical columns are called groups or families. I think families are easier to remember because they share similar properties, just like people in a family share similar properties. Each family is also designated by a number and a letter. Any group or family that ends in an A is what's called as a representative element. And the representative elements are called that because they kind of represent the range of properties that we see on the periodic table. That's where we're going to live for most of the year. The elements that end in a B are called the transition metals. Those are the ones in the middle. Those are not your representative elements. So, periodic law. This change in properties as we move from group to group is called the periodic law. It officially states that when elements are arranged in order of increasing atomic number, there's a periodic pattern in their physical and chemical properties. Really, we need to know we've organized by atomic number, properties repeat. And this means that we do not have to memorize the periodic table. We do not have to memorize all elements that are known. We have to know a few. And if we know a few of those elements, we know that elements in the similar family have similar properties. So we have to memorize far less. There are three broad classes or groups of elements that we can say. So there's metals. Metals are the largest kind of category on the periodic table. Most elements are metals. All metals have high electrical conductivity. They're shiny. They're ductile and malleable, so you can bend them without them shattering. And with the exception of hydrogen, every element on the left side of the periodic table are metals. Even the transition metals, hence metals. So certain groups on the periodic table that are metals have specific names. So for example, group 1A are called the alkali metals. Group 2A are called the alkaline earth metals. You will need to know those. What we actually find is that the elements that are not group A metals are also metals, transition metals, rare earth metals, things like that. Now, in the upper right-hand corner of the periodic table, we find the nonmetals. Nonmetals are generally non-lustrous. They're not shiny. They're poor conductors of electricity. Really, the name says it all. So you have your metals, and then you have nonmetals. Think about all the properties of metals, then put the word not or non. Metals are shiny. Nonmetals are not shiny. Metals are good conductors of electricity. Nonmetals are not good conductors of electricity. They can be gases at room temperature. Some are solid, one's a liquid. And there's two important groups of nonmetals. The far right side of the periodic table, group 8A, are called the noble gases. Very, very non-reactive. Um, up until relatively recently in history, it was thought that they were entirely non-reactive, but we now know that they're not. They are just very non-reactive. They can react, but only under very specific circumstances and generally do not. The second from the right, group 7A, are called the halogens, which are extraordinarily reactive and pretty much universally quite dangerous and toxic to humans. Finally, separating the metals from the nonmetals is a border group called the metalloids. And I love the metalloids because they are the border between the metals and the nonmetals. Their properties are the border. They mix and match the properties. So for example, silicon is kind of the poster child for metalloids. Elemental silicon is shiny. It looks like a metal, but it's brittle like a nonmetal. So very, very interesting in that case.